Hello everyone. In the last couple of videos I showed you how to make a TCP client using sockets in C. And that consisted of using getaddrinfo to call DNS and find the IP address associated with the host. And then we called connect to that particular IP address and port. And then I showed you how to use send and receive to send bytes and to receive bytes over the socket that we had set up and connected to. But what I didn't show you is how to create a server on the other end. And I would like to show you that now, how to do that programmatically in C. And to do that, let me actually just take this file and copy and paste it, because a lot of the steps are going to be pretty similar. We're going to start off using getaddrinfo again. And we're going to use some of the same methods to set up the socket. But there's a couple of key differences here. So one of them is we don't have a host this time. We are the host. So this parameter is going to be null. The other thing is I have to, in my hints to getaddrinfo, so when I'm saying, okay, this is what I want, these are the parameters I want to set when you're looking for a valid configuration to connect this. I have to set a flag that I didn't send before, and that's going to be called AI_passive. So what this says is address_info passive. This is new, and what I'm saying is use my IP, and this is very important. If I don't say this, it's not going to work. So on a server, I want to use my IP address. I'm listening on my IP address to make a connection. But otherwise, the parameters here are the same. Let me just, for the port, let me just make a variable for that up here. Actually, I'd like port 60,000 because that's the highest multiple of 10,000 that is a valid port number. Okay, so those are the changes I had to make. I had to say I want you to actually use my IP address, and there's no particular host. I am the host, so that parameter turns out to be null there. Okay, but then I'm going to go through and I'm going to try to make the socket again. Let me clean this up. A lot of this stuff was just for printing before. The important thing that I actually need here is I need to try to connect to the socket. And so if the file descriptor is not -1, that means it was successful. There is actually one more thing I want to do here this time, because if I'm listening on a server and I kill the program, and then I launch it up again, I don't want that socket to get locked out if the program didn't shut down in an orderly way. So I'm going to set this parameter, say set sock opt on this socket file descriptor. And I'm going to say sol socket so reuse addr. So we can reuse this address. And actually, it's kind of funny. When you set these socket options like this, you have to define an int that says, okay, am I going to set this flag to 1 or 0? And you have to give the memory, it's so weird, you have to give the memory address of that int, and then you have to say, okay, that int is 4 bytes, or however many bytes it would be, large. So that's what we'll do. Like any other of these socket system calls, this will return -1 if there was a problem. So if that happens, I'll just put something out here. So I'll say error setting reuse address. Let me print out the error number. But I'll keep going. That's just like, this is something that's kind of to help me out if I'm running this program multiple times. Okay, but otherwise it's kind of the same. I just go through until I find an IPv4, IPv6 configuration with whatever protocol. Go through until I can actually set up a socket like that. If none of them worked, then I make sure that I exit in an orderly way here, freeing the dynamic memory. If it did work, then I try to connect to it. But it actually doesn't really make sense to connect, because what am I connecting to? I'm actually the one who's supposed to be listening here. So instead of connect, I have to do a sequence of 2 other system calls. The first one is called bind. So what I'll say is here set up stream on socket for listening. And step 2a is bind my IP address information to this socket. So let's just look at the man pages for bind real quick. So bind is supposed to take the IP address that we're binding this to listen. And that's it. Okay, so that's something that we would have gotten from this successful node here. So let me do that. So I'm not going to connect. So let me actually, and actually I'm not going to send the messages like this. Let me get rid of this stuff. But let me instead do a bind. So I'm going to say, okay, let's try bind. Thread equals bind sock fd, and then it's going to be node AI ADDR and node AI ADDR len. And then we can still print out this error here if there is one. So I'll say, okay, if that was a problem, I'll say error number blah binding to socket. Okay, so this is where I actually let the socket know what my IP address is. And saying I'm going to bind and listen on net. So let's just try that. All right, everything seems okay so far. After that, though, I need to do one more thing. I need to call a system command called listen. So listen marks the socket as a passive socket. And so this is the last thing we need to do to set this thing up to listen, as the name would suggest. So let me, actually, let's see, at this point, I don't even, yeah, okay. So if I made it this far, after I try to bind to this, I can go ahead and free the address info because I don't need that anymore. So I'll free the address info, starting at the beginning of the linked list here. We can just make sure that that compiles. That was something I forgot in the last video. I put it in the end. Let's just make sure there should be no memory leaks here. Okay, no memory leaks, that's good. All right, so last thing I do here, I'll say step 2b is listen on socket, so, or really mark the socket for listening. And if we look back at the man pages again, we see that it only takes two parameters. The first one is the socket file descriptor, the second one is backlog. And this is how many people can get in line to try to connect you before you start dropping them. So we just define the backlog here, maybe I'll say 10. And so let me say, okay, let's try this. I'll say ret equals listen on that socket file descriptor with that backlog. And if there was a problem, I'll say error number blah listening on socket. Okay. So let me just compile that, make sure it works. Okay, so it seems like we're in pretty good shape so far. Okay, now we are finished setting up the socket to listen for incoming connections. And it's ready to accept an incoming connection coming from a particular client. And let me show you in a picture what happens here. So if a client comes along and wants to connect, let's say Chris comes along and wants to connect. Well, Chris is first going to connect to this listening socket here. And that listening socket is going to do a, while behind the scenes what's happening is TCP is going to do a three-way handshake to set up a full duplex or two-way connection between Chris and the server. That new connection is actually going to be abstracted by another socket, a different socket here. So I'll call this the Chris socket. And that is going to be a different socket from the listening socket that is devoted just to this client-server communication here. And actually at this point it's just a two-way communication. You can send and receive in both directions from Chris to the server or from the server to Chris. And that's a different socket. And so then somebody else can come along. Let's say that Theo comes along and wants to connect. Okay, so Theo connects to the listening socket, gets in line. Listening socket accepts Theo's connection, makes a new socket for Theo, and then sets up a two-way communication on the Theo socket. Okay? So once we're listening, we're able to set up these new two-way TCP connections. We're able to negotiate these with this three-way handshake that's going on in the background. And so the method that does that is this method called accept. So let's look at the man page for that. So this is going to be a method that takes in the listening socket, the socket that we're listening on, and then it takes a pointer to address information of the person who's connecting to me, as well as the address length of that. Now we did something kind of similar to this in this socket here. We had this struct sock ADDR in general. So I can say, okay, struct sock ADDR their address. Just make sure that I got that right. So, yep, okay. And then I'm going to also say struct, I believe it's struct sock ADDR len. Actually, hang on, I got to check this. What was it here? I had the length of the socket address. Let's look at the man pages real quick. So I'll say man sock ADDR. This is sock len t, I believe. Okay. So let's try this. I'll say sock len t is equal to size, or I'll say ADDR len is equal to size, or yeah, size of their address. Okay, finally, I think I have all the parameters set up here. And so what I can do is call this accept method. So I'll say int client sockfd equals accept sockfd their address, and then let's see, the last parameter, is it a pointer to it, or is it? It is a pointer to that. Okay, so pointer to the address length. Okay, now this is really interesting. So the accept method, or the accept system call, it blocks. So this is going to wait for an incoming connection, or wait for an incoming connection on sock FD. Okay, so on the listening socket that I was depicting in that picture. But if everything went well, this accept method is going to return a new socket. And that's the socket that we're going to be able to have this full duplex communication with the client that we're connected to. In the meantime, we can also find out information about the address. But again, let me first just make sure this compiles. Okay, that compiles just fine. Let me crib some of the code. Oops, I should say this first. Hang on. Okay, yeah. Let me crib some of the code I had here that was looking at just printing a little bit of information about the connection. So yeah, this should be using the same type of IP address as the listening socket. So yeah, I will just cast this. So I'll say here, this is their address, and same thing here, their address. So I'm just going to print out the IP address of each of these here. And okay, so let's just make sure this compiles. Okay, so what I'm going to do here, let me run the server. Actually, let me go back over the client too and make sure. Okay, so I'm going to connect here to my local IP address at port 60,000, and that is also the port that I'm listening on here. Yeah, okay, let's see what happens here. I'm listening on this server. Let me open up a client here. So let me compile this client here. Client.c. Okay, so the client connected, and I see on this end actually the server closed here. I didn't print any information about the IP address though. Somehow it missed both of these. Let's see, did I? Oh, it's because I think I already freed. Whoops, I freed the address info too soon. So let me not free that until the very end here. So I didn't know if it was supposed to be IPv4 or IPv6. So let's try that again. Let me throw the client back over there. Okay, cool. So it tells me the IP address of the incoming connection is 127.0.0.1. That's because I'm connecting to myself right now. But, you know, this is the IP address of anybody who's connected to me. Let's say IP address of new connection. Or maybe I should say got new connection. So after this accept method finished, I'll say, you know, assuming that the socket is valid, then I'll say got new connection. Got new connection. And then we'll say what the IP address is. All right, so that'll print out some nice info there. Of course, we want our semicolons here. All right, try that one more time. It says got new connection. IP address 127.0.0.1. All right, good. So that seems like it's working. And now we can communicate over the socket. So what I can do is, all right, I know this client is sending some information. Let me actually receive that information. So I'll make a little buffer. I already defined this buffer length thing up here. Okay, so I can get rid of this stuff now. This is, I guess I'll say here, this is step 3, accept connection and communicate. Yeah, so let's see what we're getting over the server here. Let's see what the client is sending us. So I'll say, okay, char buffer, bufflen, and I'll say, yeah, let's go ahead and receive. If you remember, the way this works is first parameter is the socket I want to receive over, second parameter is the buff, third parameter is the buff length, fourth parameter is flags. So in this case, I actually want to receive over, actually I better put this in here. This only makes sense if the client socket, this new socket that got returned here, that I was depicting in this picture, it only makes sense if that socket actually worked out, if that socket's valid. If it is, then I will receive on that socket. So very important, common mistake. Some people might still want to receive on the listening socket, but that socket is not the socket that we're going to communicate after the three-way handshake. We're going to be communicating with this new socket that was created just for us, just for this client-server connection here. So that I called here client socket FD. It's the one that's returned from accept. So I want to read into buffer over that socket. I'll read up to that many bytes, 0 flags here. So let's see what we got. So I'll say received the string. We should spell receive properly. And yeah, let's see what happens. Did we actually get a server that works here? So let me compile this. And now when I run this program, it tells me that I sent 29 bytes. And actually, it received them here. Received, hello remote person 475. Great. So we were able to get information to our server from this client. Okay, one thing I forgot to do here that's important is I definitely want to close this socket when I'm finished with it. I was already closing the overall listening socket. Okay, but there's a bigger functional problem with this. If I go back and I run the server again and I run the client, so the client does its thing, closes down, server does its thing and closes down. But what if we want multiple people to be able to connect to the server? Right now it's kind of one and done. The first person that connects, they get service, but then the server closes. Well, we want to make kind of a multi-process or a multi-threaded server that can service multiple clients at the same time. And there's a couple ways to do this. Beej's guide, which I'll link in the description, talks about how to do this with processes, forking off different processes. So I'll show a different way. I'll show how to do it using threads. It depends on what you're looking for, which one you want to do. The advantage of threads is that the different client services can have shared state, if that's important. Okay, so let me show you how to do this with threads. And basically, the difference here is I'm going to, for now, I'll just be a little bit sloppy and put this in an infinite loop. But let me... Yeah, so I'll never get down to these statements. So this is not what you want to do ultimately, but just for the sake of demonstration, I'll do this. And so the idea is I'll go in an infinite loop, And you know, I might have some backlog of people who are waiting, so, or they could come up anytime. And what I'll do in this loop is just, hey, whenever this is ready, I'll accept a new connection, and I'll send this connection off to some thread to be serviced. Okay, so threads are little programs that can run at the same time. And they use the same memory, but they can actually run on the same core. Ideally, they'll run on different cores and they'll go faster, but it's just a way to have multiple different things running at the same time in the same program. So for this, I'm going to use POSIX threads, and that's pthread.h that I got to include here. And so the way that this works is, okay, what I'll do here is every time I accept a new connection, I'll print out information about it. But any work that I do with this connection, I want to do within the thread itself. So I want to make a new thread and then send off information to that thread to be processed. And the way that I have to do this is by defining a first thread object, pthread _ t thread, and I need to call this method called pthread create. So let me just look at the man page for that real quick. Pthread create. And so this is going to take a pointer to that thread object. And then there's some other additional attributes I can set, which I'm not going to, so that'll be null. Then it takes actually a function pointer. So a pointer to a function that takes one parameter, which is a void star, and that returns a void star at the end of it. So I have to, okay, let me set that up. I'm going to have some method that does the work. So maybe I'll call it service client. Okay. So that is what it's telling me, the function prototype that it needs. And then the last argument is just a void star, which if I want to provide it, that's the single parameter that would actually get passed along to this thread when it's created. Yes, so let me try this. If I say pthread create, as I said, the first parameter is a pointer to the thread. Next parameter is some options that I don't need them. Next parameter is a function pointer. So I'm just going to say service client. Interesting, I'm passing one function to another function, right? And then the last parameter is a void star. And that can have any parameters that I want to set this up. Now, one of the things that's a bit annoying about this is if you want to pass along multiple parameters, you kind of have to pack them into a single variable. So maybe I'll show an example of how to do that. I mean, you would have to define some kind of struct. Maybe I'll say struct thread args. And I certainly want to know that the socket file descriptor, right? Maybe I'll pass along one more piece of information. I don't know, let's say maybe I'll pass along, just for the sake of it, I'll pass along the port, even though I'm not going to need that at this point. Okay, and I don't know, maybe I'll also pass along a counter or something. Maybe I'll count how many of these that I've created. So I'll make a counter, I'll start off at 0. And so every time that I'm ready to make a new thread, what I'll do is I'll instantiate, or I will dynamically allocate memory for a new one of these. So I'll say that equals, so I'll say, actually I guess I'll call it targs for thread args. I called it pargs up here before. But yeah, okay, so I've got sockfd, port, and thread number. Oh, don't forget my semicolon here. So just to remind myself, I'm going to put this down here real quick. Yeah, so what I'll say is, okay, this is equal to that malloc size of that. Okay, so yeah, I'm going to dynamically allocate this because I'm going to pass it off to this thread, and let's say that the loop immediately went to the next client that was waiting in the wings. Well, then this would be taken off of the stack. If this wasn't a dynamically allocated variable, this would be taken off the stack, and I might lose it before I had a chance to unpack the information in the server thread. So let me dynamically allocate this, and when I'm finished with it, I'll free it up here. You know, I'll unpack information, then I'll free it. Okay. So actually, when it makes its way up here, I have to actually cast it differently. I have to say void star, or I have to say struct thread args. Yeah, I'll say targs unpacked or something. I do have to, because this is a void star, that's a general way for these thread methods. It doesn't know what type it is. I need to tell it what type it is in order to be able to dig into these variables. So yeah, let's say I do that. I'll dig it up here, and I'll definitely get the socket file descriptor unpacked. And I don't need the other stuff, so I'll ignore it for now. But that's just to show you how to get multiple arguments into the thread. Okay, so when I'm done with it, then I can free it. So I dynamically allocated it down here, but I'll free it up in the worker. And yeah, actually, let me put the information in here too. So I'll say, okay, I want the socket file descriptor to be the client socket file descriptor. And yeah, for the heck of it, I'll just show you, even though I'm not using this information, I'll just say targs port equals port, targs red num equals counter. I'll say counter plus plus. Okay, whatever. Great. And so then what I do is I just go ahead and pass along that argument to the worker thread. And so what I'll do is this is stuff that I want to do once the thread has started. So let me move this up. So this receive. Let me move that up here to do some work. And yeah, okay, so I'm calling it sockfd up here. And I've decided to close this. And actually, when I'm finished, I should call this method pthread exit to close down the thread in an orderly way. You know, it gets a little bit trickier if you don't know exactly, like let's say somebody does a keyboard interrupt and some of the threads are still running. Well, you have to, there's more work you have to do to keep track of the threads, but I'm going to keep it kind of simple now and just say, hey, these threads do their work and then they're done. All right. So we'll just keep it simple. Let me make sure that I can compile this. So let's see, server.c. Okay, cool. It actually worked. All right. So now, okay, since I have set this up to go in an infinite loop that just keeps listening for new connections and accepting them, and then sending them off to the thread to do their work, I should be able to continue running the server and connect to it multiple times. And actually, just to make sure everything made it up here okay, let me, in the service client method, I'll also just say printf servicing client blah. So I'll say targs thread num. Okay. Yeah, I don't know. I called it client or thread, whatever, same thing here. There's a one-to-one relationship between the different clients and the threads. Okay, so let me compile this. Whoa. Hang on a second. I meant to say targs unpacked. Okay. Good. All right, so let's run the server. It's waiting. And now I run the client. I got something here. But look, it's still running. Now I can run the client again. And I can even change what the client says. Maybe I'll recompile this. I can recompile it in the meantime and say, okay, I'm running something else. And now if I compile the client, it'll run that through. And it says, oh, I'm ruining something else. Okay, close enough. Nice. So this server is going to continue to go infinitely. So if I want to stop it, I should type Control-C. Oh, and one more thing I should mention. On some systems, you may have to explicitly link to the POSIX thread library. Under Unix, usually it's LP thread, you would say that when you compile. It depends on what operating system you're running. Okay, so there is your basic multi-threaded server. Of course, you have to be careful to clean up the stuff properly. Right now, this doesn't get hit if I do a keyboard interrupt. It never makes it past this infinite loop. So you got to be a little more careful about a couple things, but this is enough to get you started. And what I'd like to do now is talk about a couple embellishments that you can do to make this even fancier and more functional. So one of them is, right now we're sending plain text messages from the client to the server that are in ASCII. But it can also send binary data. And in fact, this is what a lot of protocols do, like DNS. So how do I do that? Well, actually, it's quite convenient in C using structs. And so let's say that I made this message.h file that I'll share between the server and client here. So let me include this up here. Include message.h, and same thing in the client. So I'll share that some information between the two. And let's suppose that my program was just going to send like somebody's username and a message. Okay? And so what we should do is come up with a header that has different pieces of information. And so maybe the username can be up to 2 bytes. So maybe the first part of the header I say, okay, what's the length of name? And that could be up to 2 bytes. So I'll say this is byte 0 here, this is the beginning of byte 2. And then let's say that the message could be really long. Maybe I'll use 4 bytes to store the message length. So length message. And so that brings me up to byte 6 here. And just for fun, let's try to get to lucky 7. Let me have a magic number at the end of this. That's just 1 byte. So maybe I'll say magic number. I'll say magic number. Or actually, let me write it out as it is. Magic number. I just have to make the font smaller here because this is only 1 byte. Okay. Okay, so let's say that this is my header. And this is going to be in binary, actually. I'm trying to make this look like it's only 1 byte. Okay, whatever. Close enough. So yeah, I need a 7-byte binary header, and that's something I'm going to send over the socket from the client to the server. And then after that, I'll send the actual body. So this is really the header here. And then I'll send over the body, which will contain, first I guess I'll send the name. I don't know how long that is exactly. But after I send the name, then I'll send the message. So here I have my name. I don't really know how long it is, but the client will know how many bytes to ask for because I will tell it how many bytes the name is. Okay, so once that comes through the wire, I will then send over the message. And I don't know how long that is either. But so here's my little protocol. So this is a very simple protocol that I'm coming up with here for sending messages. Okay, so let me define this header. And so I'll say, okay, I'll call it just header. I'll call it struct header. And I'm going to say, okay, the first thing is a 16-bit, 2-byte length of the name. And then the next thing is a 32-bit or 4-byte length of the message. And it's very important that I put these in the right order because the struct is actually going to lay them out in that order in memory. And then finally I put in my magic number. Okay. Now there's one thing I should do here to be safe. Sometimes, I'm not sure if it might happen here because of this 1 byte at the end. Sometimes it's the compiler or the runtime will put in padding. I guess the compiler would put in some padding into these. But I want this to be exactly 7 bytes, and I want them to be lined up exactly like this. So just to be safe, I'm going to throw in this thing, attribute packed. And that's going to make sure there's no padding. Okay. So I'll say make a struct with no padding. Now let me make sure this compiles. I might need to include something up here to use these types. Let me see. Okay, actually compiled. That was all right. Great. Okay, so let me go to the client actually and set up something that I'll send here. So let's say I came up with my name, and yeah, I'm not gonna receive a message here. Maybe for now, just for this example, I'll just have the client send something, and I'll have the server receive something. You could have it go both ways if you wanted, but just in the interest of time, I'll just have it go one way. So let's say, okay, that's my message, and then I'll also come up with my name as Chris. And So let me now set up my header. So in order to do that, I should compute the length of my name and the length of this message here. So I'll say, okay, uint16t len name is equal to strlen name. And then uint32t len message equals strlen message. And now let me put this information into a struct for the header. So I'll say struct header, and I'll say header.len name equals, now here's where I gotta be a little bit careful. So you might just think, okay, cool, I'm gonna put, length of name right in there. But remember, I've talked about this in other videos. My processor is an Intel processor, and it stores these 2 bytes in little endian order. But we always want to put things in big endian order when they go over the network. So I have to use this method, host to network h2ns, host to network short, to convert this into big endian format to go over the network. All right? And I'll have to do a similar thing for the length of the message. In this case, it'll be h2 network long for the length of the message. So this is 4 bytes, and so it needs to use that method instead. Okay, so this is little endian versus big endian. And I'll just say, my magic number, maybe in this case, magic number is equal to 475, since that's the class that we're in. All right, so let me go ahead and I will send over first the header. So I'll say send over this socket that I've established. So this will just be, the memory address of the beginning of header here. And I know it's 7 bytes, but just to be safe, I'll say size of struct header. Okay, so that's going to send over the first 7 bytes in this case. Of course, I should check the return code to make sure it actually did send over 7. So let me just check that. So I said for header, sent over blah bytes for header. Let's make sure that that was actually 7. Then I can go ahead and send over the name, because that's the next thing I'm expecting in my little protocol here in the body of the message. So I'll say send sockfd name, and I know that that is going to be len name bytes. Not doing anything special there. So I'll say send over block bytes for the name. And then finally, I'm going to send over the message. Okay. Message, len, message. And so these are going to end up in some buffer on the client side once they make it through the transport layer. Or sorry, these are going to end up on a buffer on the server side once they make it through. And then I have to receive them and unpack them. So actually, let me just make sure this compiles real quick. Oh, that's funny. The magic number was bigger than the biggest it could be was 255. So okay, I have to choose a different one. I'll choose 174 since that's the class that everybody started with me. Oh, that's funny. Okay, anyway, but I think everything else is okay. So we're sending over the header, then we're sending over the body in 2 different messages here. So back on the server, what I have to do is realize that, okay, the first thing I'm going to be receiving is the header. And so now I'm going to receive into this header as many bytes as there are in the header. So I'll say size of struct header. And actually, before I go any further, let me just make sure that I am getting the information over here properly. So let me just print out what I got. So I'll say, okay, len name equals blah, len message equals blah, and magic number equals blah. And I'll just quickly print those out. So it's header dot name, header dot len message, header dot magic number. Okay, so let's compile the server and see. So I've got the client there. Okay, that seems okay. So if I run the server and then I run the client, what happens. Okay, so the client tells me to send over 7 bytes for the header, 5 bytes for the name, 31 bytes for the message. So on the other end, okay, something's going wrong here. What did I miss? Okay, so this would be a big problem if I'm like, oh, okay, I need 1280 bytes for the name and I need that many bytes for the message. Okay, so people who are watching this who are paying very close attention, you see that, I converted it to big endian as I sent it over. I need to convert it back from big endian to little endian if that's what's happening in my processor. Once I've received these 7 bytes into the header, I need to convert those back. So I need to go to the 2 bytes for the length of the message, and I need to say network to host short header dot, or sorry, that's the name is 2 bytes. Network to host short for the name, and then len message is network to host long. Oops, let me say header.len name, and this is header.len message. Okay, let's try this again. So I'm glad I checked before I asked for that many bytes. So we're going to try that again. Okay, good. Now I got the 5 and the 31 and my magic number 174. Okay, great. This all looks good. So what I can do is, now I know exactly how many bytes I need to ask for to get the name. So I can do that. So I'll say, well, I guess I can allocate the number of bytes I need. So I'll say, okay, name, char name is equal to char malloc header.len name plus 1. I'll make enough space for the null terminator. And then what I'll do is I'll receive into that. Sure. I know I want to get header.len name bytes. I'll make sure that the last thing is the null terminator. Okay. So that's the name. Let me just try and make sure I got that. So I'll say name is blah. And I'll say, okay, let's print that out. Let's make sure the name came through okay. And let's try this again. Okay, so name came through, Chris, wonderful. Of course, I should free, as soon as I'm done with this, I should definitely free this dynamic memory I just allocated. So I'll say free name. And then, do the exact same kind of thing for the message. So I'll say message here, that's going to be the length of the message plus 1. Receive into message, as many bytes as there are in the message. And make sure that the last character is a null terminator. And maybe I'll put some quotes around the message to make it exciting. Change that to message as well. Okay, I think I've got it. Make sure I remember to free the message. I like to free things in the reverse order to how they were allocated. Okay. Let's do that. Yay! The message made it through. Oh, and I sent the line break, so it looks a little weird with the with the quote there. Did I send? Yeah. Okay, so I sent a line break. Okay, fine. So it works. So yeah, this is a really nice way. I mean, it seems a little weird. Like we have to do this extra step to make a struct to get this data in binary, but often that's a much easier way to communicate headers for different protocols because you don't have to parse them. I mean, the struct does the work of parsing them for you. The only thing you need to do is just be mindful of these endian conversions. But otherwise, it's pretty straightforward. So anyway, I really like this way of using structs to send bits of information over the network. Okay, there's one more thing I want to tell you about that's really important. If you have a multi-threaded server, sometimes you want to share variables between the different threads. For example, like in a multiplayer game, you might want to have a state of the game that's consistent among all of the players, each of whom is a different client. And in that case, we need to be very careful because when we share variables between threads, we don't know the order in which what thread will access them. And it's totally non-deterministic. So we can lead towards race conditions if we're not careful. And so I'll just show a really simple example of a variable that's shared among threads, and I'll explain one strategy of dealing with that. And it's probably going to be okay in this case, but let's suppose that I made this counter that I was using to keep track. Instead of making an argument in a thread here, I'll make it a global variable, and I'll say counter plus plus in the worker thread here. So the threads are going to share this variable. I don't know which one's going to get to it first, so it could end up coming out of order of what the connections come in, or it might just have a race condition that causes it not even to be incremented properly. Okay, so we'll do that. Yes, let me get rid of it down here. Okay, yeah. Now I think this is probably going to be okay because this is a really simple example. But you just got to be really careful. Whenever you have variables that are shared between threads, there's just no guarantees that it's going to work out unless you do something very intentional. Yeah, so if I run this a bunch of times, I think it's going okay. So we say client 0, client 1, client 2, client 3, client 4, client 5, okay? But yeah, this, it's a little bit beyond the scope of this particular tutorial, but you really got to be careful about race conditions. What we want to do is make sure that only one of these threads can read to and write from this variable at one time. So basically we want each thread to be able to finish its work and block the other threads from accessing that variable until they're finished. That's one way to deal with it. And so to do that, I'm going to use something called a mutex. And to initialize that, it is called a pthread mutex t. So what I'll do, so I'm going to have each thread share a mutex. And I could make it a global variable, but just for the sake of this illustration here, I'll make it be part of the argument to the thread. So I'll make this mutex be an argument here. So I'll say pthread mutex t, and I'm going to call it lock, because I'm going to use it to lock down a variable and then to unlock it so that it can be accessed by other threads. Okay, so what I'll do is maybe I'll declare the actual mutex variable down here. And then I have to say pthread mutex init. And I don't remember exactly, these are like extra flags you can give to it, but yeah, this needs to be initialized and then cleaned up. It's like one of these fake objects in C. So here I would say pthread mutex, I believe it's destroyed. Let me double check that. Let's just see if this compiles. Oh, it says too many arguments. Okay, it doesn't need, okay, this one just needs the lock, and then we're done. Okay, good, I remembered. All right, so we initialize the lock here, the mutex, and then what we can do is make this be a part of the arguments that get sent along to each thread. Okay, so each thread is going to have access to this mutex, this lock. And up here, actually, let me just take this lock out. So I'll say pthread mutex t lock. Let me unpack that from these arguments, and I'll free the struct that I passed over. Okay, so now I have a pointer to the lock that I can use. And anytime I read from or write to a variable that can have a race condition, I'm going to lock the lock associated to that variable. So here I'm going to say pthread mutex lock that lock. So it needs a pointer to the lock that we're locking down. And when I'm finished, I can unlock this. And so what will happen is, if two threads ask for the lock at the same time, one of them is going to get it first, and then this will block on the other thread. This will wait until it's unlocked. So only one thread can do these two operations at a time. So let me just, I don't think the behavior is going to change at all, but let's just see if this works still. Whoop, server. And I'll run the client a bunch of times again. And everything seems fine. It's basically the same behavior. but I at least wanted to illustrate how you would use a lock here and how to pass it along. Now, one thing you've got to be extremely careful about with these locks is don't forget to unlock the lock. I mean, let's say, something could happen here. Let's say the code crashed and this thread crashed before it could unlock that variable. That's going to be a big problem. So let me show you what will happen if you just forget to unlock or it doesn't unlock for some reason at runtime. So if I were to do the same thing where I run the clients over and over and over again, from the client perspective, everything seems fine. They're pushing things to the network. But on the server side, we get stuck. So the first one's okay, but it never unlocked its lock. And so the other threads get started here, but then they freeze at this step because they're never able to unlock the lock. And so even though the TCP has happily filled up the buffers, we never get down to actually receiving from the buffers or printing anything out here. So very important to make sure to remember to unlock when you're finished. Okay, so be nice. Give that lock back to other threads. Okay, but this is a simple but comprehensive example of some of the things that you might do when you're creating multi-threaded programs in C. So I'll provide the code in the description, and I hope that's helpful on homework 3 on the proxy server. And let me know if you have any questions. Enjoy. Oh, actually, there is one more thing I want to show you while we have the opportunity. So we've generated some pretty interesting traffic here by sending over binary information. And I would like to pop in a wireshark and show you what's going on. So if I listen on my local loopback connection, I'm actually running the server right now, but nothing's happening because nobody's connected to it. But as soon as I run the client here, I get a whole bunch of traffic. So let me stop this and look at it. So first we see something called the three-way handshake, which I mentioned before. This is something for TCP communications. That's on the stream socket we set up. What happens is the client sends something called a SYN packet with its initial sequence number. That's what it's called here. And the server then sends back, and actually we should look at the ports here because I connected onto port 60,000 on the server, but actually the client got assigned some random IP address. So the IP address of the client is 42992. That's how we can tell them apart here because they're actually to the same IP address. So this is a very simplified example. Usually the source and the destination IP address would be different. They would actually be over some network, not my local loopback. But I can tell that the client from the server here because the client has this port and the server has port 60,000 that I set up. And the IP address of the server, the IP address of the client, and the port of the server and the port of the client, that four tuple, those four pieces of information uniquely identify a full duplex connection back and forth. Okay, but this full duplex connection needs to be negotiated up front. So as I was saying, first the client sends this SYN packet with its initial sequence number. The server then sends an acknowledgement 1 byte further than that sequence number, and it sends its own sequence number along with SYN. Wireshark is showing the relative sequence numbers here. But actually, if I dig into this a little bit, if I open this very first packet here, I can see that the sequence number is actually this 2 byte, pretty large number that's chosen randomly. And what the ACK will send me back, okay, so this is 50BA 1079. Well, not 10, but 1079 hex. If I look at the ACK number here, I get 50BA 107A. Okay, so we went from 79 to 7A. So just to show you that the server gives you the an acknowledgement of that SYN sequence number plus 1. Okay. So, right, okay. Then it sends its own sequence number. So it's both an ACK acknowledgement that the client wants to initiate a connection and incrementing the sequence number, waiting for the next byte. and it sends its own sequence number on a SYN here. So this is a SYN ACK. So its own sequence number is 4F16A0FD. And then so finally the client's going to send back an acknowledgement. Let's look at the acknowledgement here. So 4F16A0FE. So again, it increments it by 1. So this is called the three-way handshake. Basically, they're getting their sequence numbers of these buffers that are going to be filling in as information is sent through. They get them all negotiated. You got to send the sequence number from the client to the server first. The server has to acknowledge it and send its own sequence number, and then the client has to acknowledge that sequence number. And then they're ready to start sending information back and forth, which is numbered according to how far it's coming along in these buffers. Now, the first thing we do on the client is we send over the header. The header is 7 bytes, right? It's got 2 bytes for the length of the name, 4 bytes for the length of the message, and 1 byte for this magic number. In the client a second ago, I said, okay, it's going to be 5 bytes for the name and 31 bytes for the message. So let's look and see if we can spot that in the traffic here. So if I look at this packet, it's got some header information from the transport layer for TCP here, and it's got from the network layer and the link layer. But if I look at the actual data that comes through, I see, okay, the first two bytes here amount to 5, right? So this is in big endian order, and that's good. So I see, okay, that matches up. 5 bytes, that was supposed to be the length of the name. And then I have these 4 bytes that are for the length of the message. And I see the message is pretty short, so these 3 bytes are 0. And we have 1 F. Okay, so that's 16 plus 15, that's 31. So good, so we got the 31 there. And then finally, I have that magic number, which is AE, which is 174. Okay? So that's great. And then the next thing that's going to happen is the client is going to send over the name in one chunk. So if we look at, okay, so there's an acknowledgement from the server back to the client. And then we send the name. There we see it. I see it's Chris. That's the data. It's 5 bytes. And we get an acknowledgement. And then we send, I'm running something else. And then I get an acknowledgement. Okay. So I just wanted to show you, we're able to actually look at that binary data over the channel and see what's coming in. And I also just wanted to explain a little bit about the three-way handshake, how these connections are established. So basically, as soon as that three-way handshake is done, that's the moment where, if I look back at the server, that's the moment where accept returns a socket. Okay? And the socket is what is the abstraction that we have in the application layer in C here to actually do communication over in both directions from the server to the client and the client to the server. Okay, that's it. I hope you thought Wireshark was cool. And again, let me know if you have any questions in the comments.